Hi, my name is Jacqueline Dean, and this is my Lab 4 for Physics 2112, Circuits. Before we begin, here is evidence of me and my group doing this lab. You can see me clearly pointing at a Georgia Tech sticker and a Georgia Tech laboratory. And here are some pictures of our circuits with more details of those pictures later on into the lab. I did not want to lose so many points off of this lab for not proving that we did this where we were doing it. So here's this evidence. In this lab, you will use real circuit equipment found in our physics labs to complete several measurements with basic circuits. Using the principles of energy conservation, which is known as the loop rule, and the current conservation, which is charge conservation plus the definition of steady state, you will predict the behavior of circuits containing resistors in series and in parallel, use multimeters to measure the actual values of conventional currents and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. Important initial physics concepts include Kirchhoff's rule of nodes, which is the current entering equals the current exiting, the loop rule, which says that the change in V around a loop must be zero, Ohm's law, which says that V equals IR, and general knowledge in circuits in series and in parallel. For these labs, we use physical models in the Georgia Tech labs. For the assumptions for all of the experiments we ran are the resistance in the wire is negligible, the resistance of the ammeter is also negligible, the system is the circuit, and the surroundings are everything that is not the circuit. The first set of initial conditions are a circuit with 2 ammeters, 2 batteries, a 100 ohm resistor, and a 47 ohm resistor. And the second initial conditions we set up were a circuit with a 9 volt battery, 20 ohm light bulb, and a 200 capacitor. Here we can see the circuits that we set up based off of these initial conditions. These are also the pictures that we found at the beginning of the lab to prove that we actually did the lab before the report even started. So here are those pictures. Under the first experiment, we predicted that the currents will be the exact same, the ammeter will read 0.02 amps, and changing the direction of the ammeter connection will not change the reading. For these results, we found that all of these were true, and the ammeter reads 0.02 because 3 volts divided by 147 ohms is 0.02 amps. Here we can see the picture of the different sections of our circuit, and we can see the different readings. If we take 3 minus 0.96 minus 2.04, we can see that the change overall is 0, and there's the graph to accompany this data to prove that the loop rule is true. The results from the second experiment are as follows. The light dims after running the circuit. The light turns on after connecting to a capacitor. The current in the circuit slows down after disconnecting the battery and goes in the opposite way. It takes about 3 seconds to charge a capacitor using a 10 ohm bulb and about 4.5 seconds to discharge the same bulb. It takes about 6 seconds to charge the other bulb and about 8.5 seconds to discharge the other bulb. Some causes for discrepancies among this data are human error, bad math, bad any of the real-life surprise that we use, timing errors, rounding errors, etc. The answer to this what if question, which I will not read because I'm sick, we did do this experiment in real life, and it gave some resistance to the circuit, much more than the theoretical amount suggests. The properties of the ammeter's inert materials make the resistance greater than 0. And the final answer to the what if question is, the simplified circuit took much longer to charge due to the materials having resistance as discussed in the previous slide. This is not the case for the theoretical model of the circuit as done in VLab. Thank you so much for watching.